This lecture was organized by Dr. Alemi. We typically cannot look at all the values for a population. In these situations, a sample is made and a point estimate, like the mean of the sample, is calculated. The point estimates from a sample may be used to estimate population parameters. Statistical inference is concerned primarily with understanding the quality of point estimates. While the equations and details change depending on the setting, the foundations for inference are the same throughout all of statistics. Estimates are usually not exactly equal to the truth, but they get better as more data become available. We can see this by plotting a running mean. A running mean is a sequence of means where each mean uses one more observation in its calculation than the mean directly before it in the sequence. For example, the second mean in the sequence is the average of the first two observations, and the third in the sequence is the average of the first three observations. On the x-axis is the sample size going from 0 to 100. On the y-axis is the sample size going from 85, sample mean going from 85 to 100. The plot shows the running mean at different sample size in an experiment. Early on, there is a lot of variability in our point estimates in the mean of the sample. As the sample increases, we see that a more stable point estimate is obtained. The mean of the sample does not seem to depend on the sample size as the sample becomes larger, in this case above 75 cases. Even when we take samples of fixed size, there is a lot of variation in what the sample mean may look like. Here we have repeatedly taken samples of same size and calculated the mean of the sample. The x-axis shows the sample mean, and the y-axis shows how frequently we have observed the mean. The mean is the most often at 95. But the sample mean may be near 90 or near 100. The point is that calculated sample mean varies. This variability is captured by sampling distribution. Always think of a particular point estimate as being drawn from a distribution of possible values. Understanding the concept of a sampling distribution is central to understanding statistical inference. We have already introduced you to the concept of standard deviation for the population. The standard deviation associated with an estimate is called the standard error. It describes a typical error or uncertainty associated with the estimate. The standard error of the sample mean, note, not the individual observation, but the sample mean, is equal to the standard deviation of the observations, here shown as sigma, divided by the square root of the sample size. There is one issue. The standard deviation of the population is typically unknown. You might have already guessed how to resolve this problem. We can use the point estimate of the standard deviation from the sample. Thus, we often just use the sample standard deviation S instead of sigma. This estimate tends to be sufficiently good when the sample size is at least 30 and the population distribution is not strongly skewed. Confidence interval is a plausible range of values for the population parameter. Using only a point estimate is like fishing in a murky lake with a spear, and using a confidence interval is like fishing with a net. We can throw a spear where we saw a fish, but we will probably miss. On the other hand, if we toss a net in that area, we have a good chance of catching the fish. If we report a point estimate, we probably will not hit the exact population parameter. On the other hand, if we report a range of plausible values, a confidence interval, we have a good shot at capturing the parameter. A point estimate is the most plausible value of the parameter, so it makes sense to build the confidence interval around the point estimate. The standard error, which is a measure of the uncertainty associated with the point estimate, provides a guide for how large we should make the confidence interval. The standard error represents the standard deviation associated with the estimate, and roughly 95% of the time the estimate will be within two standard errors of the parameter. If the interval spreads out two standard errors from the point estimate, we can be roughly 95% confident that we have captured the true parameter. A 95% confidence interval means that if we took many samples and built a confidence interval for each sample, then about 95% of those intervals would contain the actual population mean. Here the sample mean is shown by a blue circle in the middle of the line. The confidence interval by the solid line. The mean of the population is shown at 94.52 with a dashed line. Out of 25 confidence intervals, 24 of them include the true population mean, but one, shown in red, does not include it. The rule where about 95% of observations are within two standard deviations of the mean is only an approximation. However, it holds very well for the normal distribution. The mean of observations tend to be normally distributed when the sample size is sufficiently large and the observations are not skewed and are independent. This graph shows the standard normal distribution. It is centered at 0. The x-axis shows the number of standard deviations from the center of the distribution. 95% fall within two standard deviations. Well, to be more exact, within 1.96 standard deviations. This fact can be used to construct a 95% confidence interval. A 95% confidence interval for a normal distribution is the point estimate plus or minus 1.96 times standard error. 99% fall within 3 standard deviations. Well, again, more precisely within 2.58 standard error. This fact can be used to construct a 99% confidence interval. And a 99% confidence interval for a normal distribution is constructed by taking the point estimate plus or minus 2.58 times the standard error. The central limit theorem tells us that no matter how the observations are distributed, the average of the observations will increasingly look normal as the sample size increases. In this situation, the 95% confidence interval is calculated as shown. The first term is read as x bar and it shows the average of the sample. This is a point estimate. The second term is a z standardized value which reflects whether we are creating a 95%, 99% or other percent confidence intervals. The last term is the standard error of the mean. The entire z times standard error of the average is called the margin of error. A careful examination will reveal the awkward language used to describe confidence intervals. Correct interpretation is that we are X% confident that the population parameter is between these two values. Incorrect language might try to describe the confidence interval as capturing the population parameter with a certain probability. Another especially important consideration of confidence interval is that they only try to capture the population parameter. Our intervals say nothing about the confidence of capturing individual observations, a proportion of the observations, or about capturing point estimates. Confidence intervals only attempt to capture population parameters. So here is the take-home lesson. The confidence interval provides a range of values that contain a true mean X% of time. See if you can do this exercise.